All right, here we have example 5 to calculate the surface area of the portion S of the cone x squared plus y squared equals z squared, lying above the disk x squared plus y squared less than or equal to 4. Okay, so first of all, this equation, when we graph it, this gives us a cone like this. It extends forever both upward and downward in the negative and positive z directions. The xy plane is right here in the middle. So this is the origin right here. But since we want the portion of this cone that lies above the disk, we really only want to keep this very top portion of the cone. We don't care about this bottom stuff. So with that being said, I'm going to go ahead and effectively take the fact that we want above the cone, or excuse me, we want above the disk. So this implies that we want, if we solve for z in the cone, we can go ahead and take the positive root of this and just have the positive root of x squared plus y squared. Technically, yes, there is a plus or minus here, but the positive half corresponds to the portion of the cone above the xy plane. So that's what we want. So we can go ahead and make that quick simplification. And now that we have that, then we can graph that. So go ahead and I'll first draw my cone. It's usually easier to draw the cone. Maybe I'll make this kind of big. Kind of looks in the middle. Okay, so there's our cone in our standard 3-space axes, x, y, and z. All right. Sorry, I didn't erase fully. This should be the positive root here. So now that we have that cone, we also want so it's the portion of this cone lying above the disk. So the disk is radius 2. So if I draw a little so there's my disk of radius 2. So if it's a disk, that means it's going to be, let's go ahead and shade this. So there's our disk. And now it's the portion of this cone that lives above the disk. So imagine we can take every single one of these points and just lift it up. And if we do that, the same distance up, then effectively what's going to happen, this is going to specify a circle on the surface of the cone. So if we lift this up, we're effectively going to get something like this. So this is specifying this cone. So this is actually the surface over which we want to integrate. So this red surface is our S. So really this is just saying a particular cone of a certain height. Because this equation, at least when we solve it for the positive root, this extends for upward. So it doesn't have a finite height. If we specify it lives only the portion living above some bounded disk, then this will specify some sort of bounded cone. So that's effectively what it's doing. So now that we have this, we want to go ahead and parameterize this surface S. So to parameterize S, the way I would approach it is the following. We started with earlier in this section with talking about how to parameterize cylinders, because cylinders are very intuitive to how we could visualize creating one by stacking a bunch of circles. Okay. Well, this is sort of the same thing. We want to stack a bunch of circles, but one thing that's different here is the radius of those circles, unlike the cylinder, they're not constant. So the radius is going to change. At the very bottom of the cone, the radius of the circle is 0, and then it's going to steadily increase as we draw our circles upward. So what I would probably think here is I know that I need to have a variable for the radius. So, and I need to have a cosine sine because I need to have circles being drawn in the xy plane. So I'm definitely going to have a cosine u and a sine u. That will draw the circles in the xy plane, or in planes parallel to the xy plane, right? If we just move this, if we just think of a plane that slides upward, then that plane will always have like a circle being drawn in it. And we're going to move this plane upward. Okay? So we definitely know that the radius of these circles that we're drawing is going to change. So let's give that the other parameter that we have available, v. So the u in the trig functions will allow us to rotate around the circle. And then this will change how big the circle is. So then what that leaves for us, we don't have a third parameter, so this z component should be automatically determined for us based on what we have here for x and y, and what's the connection between x, y, and z on this cone? Well, the connection between x, y, and z is the equation of the cone. So what we can do here is note that, let me move this down a little bit and just say here, if x equals v cosine u and y equals v sine u, then z equals the square root of v squared cosine squared u plus v squared sine squared u. And a very, very, very common feature that happens almost all the time now in Calc 3 is this trig identity. So the inside turns into v squared. The square root of v squared is v. So this component here ends up becoming v. And that's it. Now we want to know what the domain is. So let's go ahead and say for uv pairs in, well, u is going to go all the way around, so 0 to 2 pi, definitely. But then we're going to take the Cartesian product of this with, well, we can clearly see from our picture that the z value begins at 0, and then it's going to steadily increase until we get to whatever this z value is. So we definitely start at 0, but then we have to go to some unknown height. Well, let's think about this. The height, how high up we go on the surface of the cone, depends upon, well, how do we get this circle here? We get it from sort of reverse projecting, taking this circle and lifting it up onto the cone. All right? So really, if we think about this, the equation of this circle is x squared plus y squared equals 4. And that's true. This is a circle in the xy plane, but what is x squared plus y squared equals 4 really in 3 dimensions? It's a cylinder. This cylinder goes upward forever and downward forever. So really, if we want to think about this, it's actually, this circle is the result of intersecting this cylinder that we only have partially drawn because we're not thinking about it in 3D. We're thinking about this equation in 2D. But if we think about it in 3D, this cylinder will actually intersect the surface of this cone. So what we can do is take the equation of our cylinder slash circle, x squared plus y squared equals 4, and the fact that our equation of the cone is z equals the positive root of x squared plus y squared. If we intersect them, that means setting them equal or equivalently substituting one into the other. So this implies that z equals the square root of 4, which is 2. So that actually gives us what we need right here, which is 2. So at the end of the day, our surface parameterization is right here. Okay. With that parameterized, we are now able to begin tackling the problem at hand, which is that we want to find the surface area of the cone. So remember that the area of some surface S is immediately equal to the double integral of ds, 1 ds. And if we know a parameterization for S, which we do, our parameterization is right up here, then we can convert this into the double integral over our flat domain. This is our flat domain D. So let's just go ahead and call this D. Let's define to be D of the magnitude of the cross product of our partial derivatives. So let's go ahead and calculate those. So our u is the vector negative v sine u, v cosine u, 0. Our v is cosine u, sine u, 1. If we take the cross product here, Ru cross Rv, we will end up getting v cosine u, v sine u, negative v. The magnitude of which is going to be the square root of 2 times v. So the area of S is effectively the double integral over d root 2 v dA, which we can then say is square root of 2. I guess we can integrate with respect to v first. The order doesn't matter here because we are integrating over a rectangle in the uv plane. So we can have 0 to 2 v dv du, which, if you go ahead and calculate that, should give us 4 square root of 2 pi. Okay. So that's the surface area. What else do we have here? Because there was a second part to this problem. The second part to this problem was, after we calculate the surface area, now calculate this. Okay, so the only difference here is our function here was 1. Now our function is x squared z. So a little bit changes here. So the double integral over s x squared z ds is equal to the double integral over d. X squared becomes, well, what's x? On our parameterization, x is v cosine u. So this will be v cosine u squared. And what was z on our parameterization? z in our parameterization is equal to v. So this becomes v cosine u squared times v, and ds we found to be root 2v. So we can write this as the double integral over, let's see, I guess we can do the, doesn't really matter here. Let's do 0 to 2 pi, 0 to 2. This would be v cubed cosine squared u. Oop, sorry. Nope, this would be v to the 4th. All right, there's two v's here, another one and another one. And then we'll have dv du. Which, remember that when we do a cosine squared of u is just 1 plus the cosine of 2u over 2, the half angle. So you'll have to use that. And if you use that, you'll have 32 root 2 pi over 5. All right. That's example 5.